All right, everyone, welcome, and we are going to have our first PSET solution video. So I'm going to go through these solutions. If you have any questions, please be sure to comment. So what's wrong with the graph below? Well, again, grid lines, right? Axes labels, nope. Very difficult to read. A legend, and then a figure caption or a figure title that's really not necessary at all. We have an r squared value and we have an expression here, but there's no context really that's given. Again, there's a lot of empty space as well here. Figure caption is not descriptive as well. So these are all the types of things, again, that we don't want to do. And remember, we can go back into lecture 1 and see those guidelines that we want to follow in this course. All right, let's read the expert from the lab report from student. Issues with the terms accuracy, resolution, precision, and sensitivity. So remember, accuracy, the actual versus the measured value. Resolution, smallest increment of change we can measure on our apparatus. Precision, the repeatability essentially of each measurement. And then sensitivity is correlated with high resolution and precision as well. So when measuring the rolling parameter of the biodistributed interaction, the strongest, we observe a rolling parameter of this. So this is our measured value. This was a deviation from the theory predicted of 1. So already there's a difference between our measured and theory, so that's going to get to accuracy. Experiment was very robust. The deviation was this. So this is getting to, precision. So this looks to be very precise. We're able to measure biological instruments with extremely low affinity down to, so we're able to measure very, very, very small things, so the resolution appears to be good. Now, measuring low instrument was previously impossible using other techniques. We present this novel robust technique that is extremely accurate. I mean, looking at the deviation here, it doesn't seem to be that accurate. So it's not really extremely accurate. And then it says, despite what it lacks in precision, the precision and resolution here is phenomenal. So we need to correct that statement. So the precision and resolution is fantastic. It's very high resolution, very high precision. Accuracy is actually lacking somewhat. More of the sensitivity problem resolution of the field in bioassay. So basically, sensitivity is fantastic, which is, I also agree. So that's how we would want to rewrite that. Similar things going on here in this graph. There are error bars, which is great, but no axes labels here. We can't really interpret. Bad caption as well. Again, what is this data supposed to represent? So there's a lot of missing information. There's some decent things. So empty white space instead of the grid lines, which is an improvement. But we need axes labels. We need to know what's going on here. And then again, at least the previous plot was trying to do something. They were trying to show some of those values. But the key thing here is, what is this trying to tell us? So it's not basically, it doesn't stand independently, which is what we need to do. All right, I'm measuring the voltage in my outlet with a voltmeter. Nominally, so it should be 120 volts. Voltmeter measures 130, so my house is in trouble. Just kidding. Measure the voltage 100 times. The fluctuations never exceed a microvolt. Furthermore, this voltmeter can distinguish voltage measurements up to 0.1 microvolt. So it is very high resolution, very precise, very sensitive, but the accuracy is off. So again, this is what it should be. This is my actual measure. So very similar to the previous problem. So a student is conducting a lab experiment, measuring the magnetic field strength of a Helmholtz coil, which should be measuring 0.6 Teslas. The student uses a magnetic probe, measures the magnetic field up to 1 Tesla. Actually, they're using a probe that can measure up to 1 Tesla, excuse me. Sensitivity of 10 millitesla, so we're going to put that into, basically, we're going to move it over 1, 2, 3, so 0.01 Tesla. Let's just put everything here. Measures the magnetic field 178 times, sample mean of 0.5 Tesla. Measurements have a distribution that appears Gaussian and standard deviation of 150 millitesla, so 0.15 Tesla. What type of error can be occurring here? So the sensitivity of our probe is 0.01 Tesla. The error is 0.15 Tesla. So this would be our bias error. This would be our total uncertainty, which is precision plus bias. So we can see here the precision error is it's significant. So that it seems that precision error is dominating here. So there's quite a bit of precision error. So that can affect what's happening. Another student repeats the experiment, the same measurement, different probe, same claims, and same sample mean, but the error is the same for every measurement, and it's either 0.55 or 0.45. What type of error can be occurring here? Well, if there's no distribution, we know that bias error is basically predominant here. So that is effectively what's happening here, because we have a different brand. So and there's nothing here, same claims, same sample mean. So it looks like we have a different probe. It looks like the bias error is different. So compare these two measurements, which is more accurate. So if they both have the same sample mean, here, so they have the same sample mean. Let's look at the deviation. So the total uncertainty here was 0.15. This total uncertainty here looks to be about 0.05. Exactly. So we got 0.05 here. So this experiment is going to be basically more accurate because it's deviating less. They have the same sample mean, which is more sensitive. It is going to be this material, this one here, which has the higher resolution. So the resolution, which is what we observed here, this was the resolution that we observed here. So this is higher resolution than this apparatus, and which system has the highest sensitivity. Again, overall, I would say number 6 as well. Excellent. So finally, student repeats the same measurement, but with a different pattern probe, same claims, measures a mean of this, so not as accurate. Observe an error that appears Gaussian with a standard deviation of 0.1 millitesla. So again, we're going to have probably some combination of precision and bias occurring here because there's a distribution. So precision error can be going on. Does the statement seem logical? Because we have a different plan, same claims. So 0.1 millitesla means this is going to be 0.1231 Tesla. So this measurement seems extremely sensitive, and the resolution seems very, very high and very basically this system seems to have the highest sensitivity and the highest precision effectively here. So, but the accuracy is the worst. So the 3 measurements, this is the worst. This is probably the best, and then over here. So excellent. So because we're a little bit off, because we should be measuring theoretically 0.6, and it's just too tight. This one's just too tight and too off, because you're not even getting close to overlapping. Whereas over here, you're getting a little bit closer, essentially, in that overlap, in that 0.05. So fantastic. So good luck. Great job. First problem set done, and we'll see you in the next problem set solution video. Thanks.